application of an integral is to find the average value of a function. You might have heard the term average value pop up with sine and cosine functions. So if I have a sine slash cosine function that looks a bit like this, right? A lot of you already know that the period is equal to 2 pi on n, the amplitude is a, and the plus c is what we call the center, right? Or it's also known as the average value of the function, right? So average value of the function. So if they give you like a question that's like, maybe the temperature is modeled by a sine graph, and they'll be like, well, what's the average temperature? Well, that's just whatever the plus c or the y translation is, right? Well, another way we can work out what plus c is, or not plus c, sorry, another way we can work out the average value of a function is maybe, it's like some, function like this, yx squared plus 2. It doesn't fit a sine graph, right? So how do you work out the average function? Well, we can use an integral for that. So the equation for an average function is this, right? So what it actually does is, well, this integral here finds the area, and then it spreads it out using this 1 over b minus a, right? So remember the area of a rectangle, or the area, I think area in general, right, is just height times width, right? And so what we're really doing is we're doing h is equal to a over width. Area we calculate from the integral, the width is given by b minus a, right? And that finds the average height of that function, right? Which is also the average value. Cool, hopefully that makes sense. All right, let's have a crack at this question. So they want us to find the average value of 1 over x over the interval of 2 to 5. Okay, so first thing I like to do is write out my expression. Sometimes in an exam, what I would do is just write out the actual equation as well, right? So I'll have a to b. So what I mean by the actual equation is just like the average value equation, right? So I'd write this out, and then I'd substitute my values in, right? So maybe even in the question when I'm reading it, I'd annotate what a and b are, just so that when I actually answer the question, I'm not missing, key pieces of information, and I'm not just randomly putting things in places where they shouldn't be. So I annotate the question, and then I substitute my values in, hopefully correctly, and then it's just a matter of integrating, right? From that table, that integral table that I showed a while ago, the 1 on x, you can't just integrate it like this. Ooh, don't know what happened there. You can't integrate it as if you were integrating x to the power negative 1. Just simply, and you can't integrate it like a polynomial, right? If you have 1 over x squared, you can convert that to x to the power negative 2 and then integrate that like a polynomial, because you add 1 and divide it by 2, or divided by the resultant, which in this case would be negative 1. But with this, if you add 1, this is just x to the power 0, and you can't divide by 0, right? Which is why we have, well, it's not why we have, the integral being log x, but luckily the derivative of, the integral of 1 on x ends up being the natural log of x, right? So that's just the natural log of x. Let's quickly write this out like this, right? And so that's all that's being used to convert from here to here. And then we just substitute things in using the fundamental theorem of calculus. And then it's just a matter of solving. So the way that we simplified this to here was just using simple log laws. If you don't remember this, I would suggest revising it. So when we're adding two logs together of the same base and the same multiple at the front, we multiply. When we're subtracting two logs, we divide the inside product to simplify. Okay, and that's sort of it with integrals and integration. Obviously, I haven't gone into a lot of detail regarding integration. I haven't talked about the wide application type questions, but you'll see plenty of those when you guys go through practice exams and textbook questions. We didn't go through them just because this is meant to be sort of like an introduction to these topics, and not like like a deep dive into them. But yeah, definitely check out your practice exams and other there's like 8 notes resources that go through these in a lot of depth in terms of like question styles. So we've sort of given you guys all the information you need to tackle these sorts of question types, but it's always a good idea to practice these question types, right? So that when you see them in an exam, you're not sort of like panicking and you're not really sure where to go. It's just a good idea to expose yourself to a variety of questions So you can sort of draw similar connections to questions that you see in your actual exam. Okay, now to start with probability. One thing I'll sort of preface this with is that a lot of people kind of think probability is going to be their worst topic. Just simply because, I feel like from like maybe year 10 onwards, probability does get pretty hard, right? Personally, I sucked with probability. So even in year 11, I really sucked with probability. So when 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 year 12 came around, I sort of thought, maybe, I've really got to like crack in, because I've got to do well, right? And so what I did was, because I really, really sucked at probability, that's a bit of an understatement, I decided I'd do every textbook question on probability. And so if you find yourself in a similar boat, maybe you're hating probability and you're, thinking you're really bad at it, it's often just a good idea to just do every single textbook question on it. And I know that sounds insane and a lot of work, but in the end, it did pay off. I think probability ended up being like my best section in terms of both SACs and exam. Just because probability is one of those sections that's really repetitive. What tricks people, and even me still now, is the wording, right? And there's only so many question types they can ask you with probability, and the textbook generally contains them really well. So just doing a bunch of questions from the textbook, a bunch of past exams, will set you up really well for probability. Whereas with integration and other topics, they can ask you like really weird novel questions. They really can't do that with probability, and they're often just repeats of each other with different values. With that rant over, we'll sort of get into it. Okay. So what is probability? Probability is the likelihood that an event will occur, and it's always like placed on a scale from impossible to like certain. So 0% chance to 100% chance. Right. So the probability of, an event X, right, is the number of the times event X happens divided by the total number of events. For example, if I flip a coin 10 times and I want to know the probability of, getting tails 5 times, I need to flip it 10 times and measure the probability, right? Or measure, like take account of how many times tails has popped up, and then I divide that, theoretically it'd be 5, right? And so I'd do 5 divided by 10, and that'll give me the probability of getting a tails. And generally we measure probability in decimals or fractions. Sometimes you'll see them in percentages though, and so it's really important that when you see a percentage, to convert it back into decimal, right? So sometimes you'll see like a statement like 50% chance of X happening, right? But it's a better idea to convert it to decimal because those calculations are easier to deal with. Even though I've said that, decimals are kind of bad to deal with. So what I would do is in exam 1, I'd generally deal with fractions. But in exam 2, often you're given horrible numbers that only simplify to decimals in your calculator. But yeah, generally try keep them in fractions, especially even in exam 2, because they will ask you, like when you guys do exams, you'll probably see this little like text section at the start, which says, give your answers in exact form unless specified, right? Sometimes in the probability section, they'll ask your answers to 4 decimal places. But most times when nothing is specified, you need to be giving your answer in exact value or in fractions, right? So keep that in mind when doing these questions. But fractions are just easier to deal with, especially when you don't have a calculator on hand. There are some exceptions though. Another thing with probability is that it needs to, the probability of an event happening can only be between from 0 to 1, right? Which makes sense. 0 being impossible, you can't be, less certain, like you can't be less likely than impossible, right? And 1 is certain. You can't be more possible than certain, right? If something is going to happen, there's no way, like, there's no like way to increase that chance from 100%, right? Another thing is that this is just sort of complicated sort of symbols that you guys will see in the questions. But basically, this sign here is sigma, right? For those of you who haven't seen it, basically just means the sum of, right? So if I have, like the sigma of some set, that just means you're just adding every value in that set, right? So maybe, the sum of some, like the sum of Ni, where n is like a set of where I is equal to 1. Maybe like, when n is like a set of 1, 2, and 3, right? This is, the notation is not entirely correct, but hopefully this will help you get a gist of it. You're just doing 1 plus 2 plus 3, right? It's not entirely correct, but that's just the gist of it, right? You're just summing all the probabilities up, or summing all the values in that setup. And so what this whole statement is saying is that the sum of all the probabilities must add up to 1, right? So if I have, like 2 events, so if I have an event, like the probability of getting heads and the probability of getting tails, well, they both need to add up to 1, right? Like, it can't be like this, right? Because this only adds up to 0.7, and that doesn't explain what happens, the 30% time, right? If I flip a coin, I'm only going to get heads or tails, right? It's so unlikely that it just lands on, like, the ridged part of the coin, right? So for simplicity, it's always going to be heads or tails, right? So it doesn't make sense that heads or tails only occurs 70% of the time, right? Which is why this needs to also be 0.5. All right, hopefully that makes sense. So all the events, the probability of all events needs to sum to 1. This is just that sort of displayed on a scale, right? 0 is impossible, 1 is certain. These are just general terms that you don't really need to know, but I think it's a good way to sort of describe what's happening in an intuitive sense. Okay, let's just revise some key terms for probability, and I'm sure you guys would have seen these terms before, but I think it's a good idea to recap them before diving into 3-4 probability. So a random experiment is an experiment with a random outcome. So let's say you have a jar, or like a bag of socks, right? You have like 20 different types of socks with 20 different colors. You just put your hand in, you're not looking, you're just digging around, pulling out a sock. That's entirely random, right? Outcome is the result of a random experiment, the color of the sock, or in this case, the color of the jelly bean. Sample space is every possible outcome of a random experiment. So maybe in my bag of jelly beans, or in my bag of socks, I have socks that are colored red, blue, and green. So the sample space would be pulling out a red sock, pulling out a green sock, or pulling out a whatever other color I said. And an event is a single outcome. So, for example, if I pull out a like a green sock, that is an event, right? Also, let's say I'm interested in the probability of pulling out 10 green socks, or like 5 green socks in a row. Pulling out those 5 green socks in a row is also an event. Okay. Another thing that's super important with probability is set notation. I'm sure you guys would have come up with union and intersection before, and it's really useful to explain them in terms of Venn diagram, but it's also, you probably would have seen them with function notation as well. So A intersection B is a list of outcomes that are both in A and B. So what that means is, if I have a Venn diagram of A and B, the intersection is that red area that I've shaded. Union is A or B, right? So it's whatever is in A, and it's whatever is in B. So it's just whatever's contained in the Venn diagram, right? So intersection, it's good to think about it as like an and thing, where so you can see here or and and, so it's and, whereas union is an or sort of statement, right? It's one or the other in union, or it has to be both of them together in intersection. With union, we have this really nifty rule, sort of, that you can use to sort of calculate what this is. There's a cool proof you can sort of do with the Venn diagrams, and I'll sort of go through that now. So if I have 2 Venn diagrams like so, if I want to work out what the total area is covered between them, but I only know the probability of A, the probability of B, and the intersection between them, if I want to work out the union, well, it's sort of useful to like split it up into 2 sort of Venn diagrams, or two circles, sorry. So I'm going to split this up into 2 circles. Let's just ignore the intersection at the moment, right? So I know what the probability of A is, and I know what the probability of B is, right? And so I'm going to add those together, and that's what this is, right? I'm getting those two circles, and I'm adding them together, right? Now, when I do that, you'll notice that this section here and this section here, the sections that are going to form that intersection region, there's two of them, right? There's some of it contained in B, and there's some of it contained in A. And so when I overlap them, I get sort of a doubling up, right? And you can see my fingers are doubled over, right? So I get a doubling up. And to get rid of that double up, because that's not counted in a union, right? Like when you do a union of a set, you don't count double ups, right? So get rid of that double up, we subtract one of the intersections. So I have a double up, and I subtract it, and now I'm just left with, A union B. Hopefully that makes sense. And then a complement is just the opposite, right? So everything, A complement is everything that's not an A. And we can also represent that by this sort of equation, which makes sense as well. So if, the probability of A happening is like 0.8, well, the probability of anything but A happening, because it all needs to add up to 1 at the end of the day. So the probability of A happening and the probability that A is not happening must sum to 1, right? Because one of those events will happen, right? And so you just need to sort of reshuffle it, and then what you'll get is 1 minus 0.8, which is just 0.2. Okay, and a little bit more terms. I know basic probability is just a lot of memorization, but trust, once you guys get to the cool stuff with discrete, binomial, and continuous, I think it's quite worth knowing these. Okay, I potentially get a lot of questions about mutually exclusive and independent. Like, what's the difference? So mutually exclusive is if they can't occur together, right? For example, if that intersection is 0, right? So A intersection B is 0, right? So if I've got something like this. Independent events, on the other hand, are when one happening doesn't affect the chance of another happening. A really good example of that is something like me solving a Rubik's Cube in, like a minute, and the probability that it rains, right? It's likely that when I'm solving the Rubik's Cube, I'm inside my room and not affected by the rain. And me solving a Rubik's Cube faster or slower is not going to affect the chance that the rain happens, right? So in that sense, they are independent, right? Their probabilities aren't linked. Now, if they're mutually exclusive, it's one or the other. There's never an overlap. For an example, maybe it's like playing cricket and it raining, right? It's like when that intersection is 0, right? Then they're not, well, it's really unlikely that they're going to play cricket when it's raining. And, let's just, for the sake of simplicity, let's say it's 0, right? So if it's raining, they're not playing cricket. If they are playing cricket, it's not raining. So it's a bit of like a logic sort of puzzle, I guess. But mutually exclusive just means that there is no overlap. They're just two distinct events that can't, it's like a yes or a no, right? Or it's an incorrect and a correct. I guess you can be like sort of correct, but if we're just looking at correct and incorrect as like two discrete sort of things, you can't be incorrect and correct. There's no overlap, right? Hopefully that makes sense. But independent, it's just that, the chance of one happening doesn't affect the chance of another happening. Now, cool thing with this is that if you have two mutually exclusive events, their union, right? The union of A and B is just probability of A plus the probability of B, right? We don't have to subtract the A union B because that's just equal to 0, right? So it's sort of pointless to represent that. Now, a condition with independent events, right, as you guys can see here, is that their intersection is a multiplication of each other, right? So it's just the probability of A times the probability of B if A and B are independent. So a super common question type I've seen is that they'll give you two events. They'll say that the probability of this happening is like 0.8 and the probability of this happening is 0.2. Are these events independent or not? And maybe they'll also tell you the probability of like an intersection. So for example, the probability of A is 0.8, probability of B is 0.2, and their intersection, A intersection B, is equal to 0.16, right? The way you'd prove that, these two are independent events is you'd throw it into this equation. And then you'd have to show that A union B is equal to these two multiplied. A intersection B is equal to 0.8 times 0.2, which it is. So in this case, A and B are independent. But sometimes you can have a case where, it's like A is 0.8 again, B is also 0.2, but their intersection might be like 0.05. Obviously, in this case, when you multiply 0.8 by 0.2, you don't get 0.05. So in the second case here, they are dependent events. Okay, cool. So we can also show that with a Venn diagram, which I've already sort of done. We can say that this area is A, this area is B, right? And when I do this, and when I want to show how this rule works, you can see that I've scribbled in this area twice, right? So I want to subtract that area again. Sort of already been through that. It's always a good idea when you get a sample space of multiple events, if you can represent it with a Venn diagram, just because it'll make doing those calculations a bit easier. It's always a good idea to take a load off your brain, more or less, right? You don't want to juggle so many things in your brain. That's just a recipe for silly mistakes. Okay. Let's talk about conditional probability. Conditional probability, super common, pops up everywhere. Really nice question type. But, enough about me talking about the question type and how it's nice. Let's talk about how we can do these. So what does conditional probability mean? It's the probability given a condition, right? Which sounds like a cyclic definition. But let's say, the probability that it rains given that it rained yesterday, right? So I'm giving you an extra piece of information to sort of deal with, right? And that, generally works in a sense that when the event that occurred previously changes the event of, the probability of a new event occurring, right? So, for example, in this example here, you're going to roll a die, and I tell you it's an even number. So what's the probability that it's a 4? Well, let's say it's a 6-sided die. The sample space of this die is 1, 2, or dice, sorry, 4, 5, and 6, right? So that's the sample space of all the possible numbers. Now I tell you that it's an even number, right? So all the even numbers are 2, 4, and 6. Now if I want to work out the probability that it's a 4, so the probability that it's a 4, given that all of these are even, right, is, well, I look at how many times 4 happens in the original set. Well, that's just, and how many times it happens in the second set. I look at their intersection. In both, it only occurs once. In the top, I have 1, right, which makes sense. Probability of getting a 4 on a 6-sided dice is 1, right, just rolling it randomly. But it's not 1 and 6 because I've changed that sample space. I've decreased it, right? I've taken it from, just 1 to 6. I've said, well, it has to be an even number. So it's either 2, 4, or 6. And so there's 3 possible outcomes, right? So I write that down. So the probability of getting 4, given that it's an even number, is 1/3. And so that's nicely summarized in this rule here. So A given B, right? So it's written as A given B, is equal to the, that's meant to be up there, but I'll rewrite it so it makes more sense. So the probability of A given B is equal to the probability that A intersection, or the probability of A intersecting with B, divided by the new narrowed down sample space, which is given by the probability of B. Also, some of you guys would have noticed that I'm writing it, I'm not writing PR, I'm just writing P. Doesn't matter, either or, they're the same. At university, for some reason, we were just taught to write it with a P. It doesn't really matter, I guess. I'd recommend just doing whatever your teacher does. This is the way I've done it, but either or I think is fine. And considering we did it at uni, I hope it's okay. Okay. All right, cool. All right. Another way we can display things, apart from a Venn diagram, is known as a Karnaugh map. So Karnaugh maps aren't explicitly on the study design. I want to make that clear, but I think they're a really good way of sort of representing these questions, and they definitely sort of really helped me during my exam. There was like the need to do a Karnaugh map, and a lot of my friends didn't love that question. I don't like that question either, but a Karnaugh map sort of helped me get through it. Okay, so what is a Karnaugh map, or probability table, right? It's, well, we represent all our possible events, and it's really convenient for 2 events, but you can do it for multiple events, right? So you can maybe have A, B, C, right? You just need to add an extra sort of layer to it. So these boxes are just the events, right? And the boxes that sort of like intersect with them are their like literal intersections, right? So this box here is A intersection B. Here is A intersecting with not B. Here is not A intersecting with not B, and so on. So when these two add, right, we get the probability of B, right? The probability of A intersecting with B and the probability that not A intersects with B. Both of that is going to give the total sum of B, right? And same here, right? Those sum up to equal this. And then these two sum up to equal the probability of A, and these two sum up to equal the probability of A. And nicely, we expect that it all sums up to 1, right? Because B and not B must sum up to 1, and A and not A must also sum to 1. Okay, hopefully that makes some sense. So let's have a go at using it on a question. So the probability that Job rides his bike to work and it is sunny is 0.1. So we've got 2 events that we can sort of characterize here. One event is that it's sunny. The other event is that Job rides his bike to work, right? So I'm going to call that S and B. With probability questions, it's always helped me to sort of highlight everything, annotate everything, just break it down from, instead of this big slab of text, right, that's really annoying to read, just breaking it down to key pieces of information that you need and not all the random stuff. Like, you don't need to know what the guy's name is, right? What you need to know is the 2 events, right? And the numbers. So the probability that Job rides his bike to work and it is sunny, right? And, okay? So that's the intersection event between the B intersection S is equal to 0.1. So I'm going to write that in my table, 0.1 here. The probability that it isn't sunny, so not sunny, and the probability that Job rides his bike, so S intersection, not S, sorry, intersection B is 0.7. So 0.7 here. Using a Karnaugh map, what is the probability that on any given day he doesn't ride his bike and it isn't sunny? Okay, so how can I do this? Well, here is 1. And so this is just 0.1 plus 0.7 is equal to 0.8, right? 1 minus 0.8 is equal to 0.2. Now let's see if the question has given us any additional information. The probability that Job rides his bike to work and it is sunny is 0.1. Okay. The probability that it isn't sunny. Oh, okay. I think I've misread the question. Which happens. I've realized there was, from what I looked at, there was insufficient information to answer the question, which is kind of unlucky, but that's fine. So I think it said the probability that it isn't sunny is 0.6. So what this is not what I've written out here. Oh, sorry, just zoomed in. I think this is just S. The probability of not S is equal to 0.6, and the probability of B is equal to 0.7. That's my bad. I'll quickly rub this out. But yeah, there you go. You guys can see just how easy it is to misread these probability questions, lose a couple marks. So it's always a really good idea. After you tried answering the question, you sort of stuck, go back to the question straight away and try work out what mistake you've made. Okay, I still think this is correct, right? The intersection between B and S. So the probability of B is 0.7. The probability of not S is 0.6, right? So I think this is a little bit more plausible and easier to work out. So just 1 minus 0.6 here would give me 0.4 for the other event, and here is just 0.3, right? Because 0.7 plus 0.3 sums to 1. Here, I just need to do 0.7 minus 0.1, so 0.7 minus 0.1, and that's equal to 0.6, which I think is going to give me 0 here, right? If I haven't done that incorrectly. And so here, I should be left with 0.3. If I made any mistakes, by the way, with any of these sorts of questions, just throw a message in chat. Yeah. Okay, and this is just going to go through that, sort of worked out. But hopefully that makes a bit of sense. Okay. And so then we can use this table to help us answer questions, right? This table isn't just for the sake of making it, it's also for the sake of helping us answer questions. So they've said it is sunny today. What is the probability that Joe rides his bike? So sunny intersecting with riding bike should be 0.1, right? But what's also important to know is that they've sort of told us a condition. They've given us the condition that it is sunny today, right? So this implies conditional, right? Because they've given us an extra piece of information. So what we need to do is we need to use a conditional probability equation. So riding bike, given that it's S, right? Given that it's sunny. So on the top, we want to know the intersection between B and S, and I said that was 0.1, so we write 0.1. The probability that it's sunny is 0.4, and so simplifying it, we'll just give 1 on 4, or a quarter, or 0.25. But yeah, I've always found these tables super helpful for these conditional probability questions, mainly. Okay, let's talk a bit about independent events again. So, like I mentioned, if two independent events are occurring, the probability of one happening doesn't affect the probability of another happening. So if I've got the probability of, like a conditional probability, so I'm saying probability of B given A, that's, the probability of B occurring is not going to affect the chance of, the probability of A. So that doesn't affect anything. This also applies, right? So the probability of A intersection B is equal to the probability of A, the probability of A intersection B divided by probability of B is equal to probability of A, right? Which makes sense from our equation earlier, right? If you remember, I think maybe 2 slides ago, I might have quoted the same equation there. See, that's derived from the previous one. Just simply because they're not conditionally linked, right? If I tell you that, in like the last scenario, right, clearly there was some link between the weather, like it being sunny or not, and the person riding the bike. But if we go back to my example of me solving a Rubik's Cube in X amount of time, maybe like a minute, I think is what I said, and it raining outside, those are clearly not linked events. So given that it is raining, the probability of me solving my Rubik's Cube in less than a minute doesn't change, right? Okay, mutually exclusive. This is what it looks like on a Venn diagram. I sort of already mentioned that. Their union is just adding the probability, of A and B together. Oh, okay, cool. All right, another technique to know is tree diagrams. So what's a tree diagram? It's a map of all possible events, right? They're generally useful for 2 to 3 events, and not anything more than that. So event A is that first branch, and then event B is the second branch, right? And it's all given in conditional probabilities, right? Because what this is saying is that B happens given that A already happened, right? And so from there, we can multiply the probability of these two things, right, to give us their intersections. Okay, hopefully that makes some sense. Another useful note to know is that if you have something with the words and, so if I want something to happen and another thing to happen, so for example, the probability of me solving a Rubik's Cube in less than a minute and the probability of it raining, then I multiply them together. When we use or, so the probability of me solving a Rubik's Cube in less than 1 minute or it raining, well, for that you use plus. And hopefully these and or sort of things ring a bell. And is an intersection, right? And is intersection. And or is union. So general rule of thumb, if you see intersection, you're multiplying. If you see union, you're adding. But remember the intersection multiplying thing only works for independent events. Okay, random variables, what are they? A random variable, more or less, is a variable that's defined through like a function, right? But this function is defined on the outcome of an experiment, right? So it's a little bit more complicated than your standard variable, but you know, it's just complicated terminology for something that's reasonably understandable. So an example here is that if you flip a coin 3 times, your outcome, right, is going to be the set of 3 coin tosses. That's either going to be a heads or a tails, right? And so you could make a random variable, right? And that random variable would be something like I said earlier, as the number of heads that are going to pop up, right? Or maybe the random variable from my example was the probability that I solve a Rubik's Cube in less than a minute. Maybe I tried doing it, like scramble it 5 times, try solving it 5 times. And so the random variable could be, solving it in less than a minute. And here are just a couple examples of some random variables, right? So hopefully that sort of makes sense. I would recommend throwing these definitions on your bound reference just in case you have a mind blank in the exam, but I would really want you guys to memorize this sort of stuff. Okay, with random variables, they are generally represented with x, but I've used different variables all the time. Especially for spec, sometimes you get like a few different variables, so you can just use different letters. Doesn't actually matter. It's just an arbitrary thing that we choose. Same with like f of x, right? You can really use any variable you want, but it's just x seems to be the favorite variable for mathematicians in methods, anyways. So what that means, like how is it represented? Capital X is the random variable, whereas 2 is like the particular event, right? So the probability of x is equal to 2 just means that the probability that our outcome is equal to 2, right? X is equal to green is the probability that outcome is equal to some defined thing known as green. Okay, mean, median, and mode. These are definitely things you guys have seen before, but I'm going to give it a little bit of a different twist on them, especially in discrete and the other stuff that's come. So mean, please remember this symbol. It's how we represent it in methods. That's called mu. The way I usually write it is just like a U, but I start like with like a tail out the front, right? So the mean measures the center of the distribution, right? And it's also known as the expected value. Hopefully this rings a bell to an integration sort of technique that we talked about earlier, or the average value of a function. When we talk about continuous probability, this can be pretty important, so keep that in mind. It's also denoted by E of x, and E of x just means the expected value of x, right? It's because the average and the expectation are about the same. The median is the value that there is 50% of the values lie above it and 50% lies below it. So if I have 1, 2, 3, 4, and 5, the probability of 1 occurring might be 0.2, the probability of 2 occurring might be 0.2, and the probability of 3 occurring is 0.1. So then the median value is 0.3 because 50% of the probability lies sort of below it, 50% lies above it, less, right? So that's a median. Right, so in this case you've got 1, 2, 2, and 5. 2 is the most likely common thing, so it's also smack bang in the middle, so that's the median. Mode is the most frequently occurring x value, or event value. So in the case of the last thing, the last one is also the mode, right? It's going to be 2 because the most, right? The value of x which has the highest probability, right? So maybe this is like 0.05, and maybe there's a bunch of more events of just 0.05 until it all adds up to 1. So then the mode would either be 1 or 2 because it has the highest probability of occurring, if that makes sense. The mean, this is a little bit of a application style question that they can ask you primarily in your SACs. Sometimes they can ask you which of the mean, median, mode is the best definition of the center, right? And I think a lot of people would just go ahead and straight away say the mean, right? That because it's the average, right? But the problem with mean is that it's not robust. And what I mean by robust is that it can be affected, or not robust, sorry. What I mean by not robust is that it can be affected really easily by outliers, right? If I have, a couple numbers 1, 2, and 3, and also 0.00001, the mean is going to be so much lower than what 1, 2, and 3 actually are, right? Or if I have 1, 2, 2, and 5, and I don't know, like 0.0001, again, the mean is just going to be dragged down, right? But the median and the mode are just better sort of definitions of a center, right? The mode is going to obviously choose 2, which is probably closer to the center of the distribution, and same with the median. Hopefully that makes sense. Sort of a side note, but regardless, very important to understand, I think. Okay, how can we measure the spread of our values, right? Obviously, after we do an experiment, we're going to get a bunch of different values, right? How do we measure the distance between each value, like how each value varies with each other? And so that's where variance and standard deviation come in. So they're both measures of spread, right? So variance is given by the square of standard deviation, right? So we generally use variance to define a distribution. We'll talk about defining distributions when we talk about binomial and normal, right? And standard deviation is usually denoted with an SD or lowercase sigma. Probably remember me calling this sigma. That's uppercase, and this is just a lowercase sigma. So variance can also be denoted as sigma squared, right? Because var of x is equal to sigma squared, right? From that. Variance is also representative of variance of whatever variable. So if your event is shown by y, you'd be dealing with var of y and not var of x. Okay? And standard deviation is ST or sigma. So standard deviation is always the square root of variance. So that says that variance must always be greater than or equal to 0, right? Because we can't take the square root of a negative number in methods. Okay,